Should breathe. You should do your homework. All right, let me try and squeeze by you real quick here. Thank you, thank you. All right, we are in business here. All right. Okay, everybody, how's everyone doing? Wonderful. There's been quite a few questions about the homework, specifically like where are the homework assignments, like where are the problems listed? And that's always going to appear at the end of the notes. So in Canvas, I told you I provided you the notes, right? And when you open up those files, you go through the notes. At the very end is the homework assignment. And sometimes I will adjust those. Like today, you're going to see that I've modified the questions you're supposed to do. So our official homework assignments will always be given here in class at the end of class. So if you're not here, if you're confused as to what to do, then you actually have to go online and go to YouTube and go to the end of the video of the class and look up the problems. So, all right, that's the deal. That clear? All right. Does anybody else have the bonus question? I know I had one person. You put it over here. What bonus question? What the heck is this? Where did this come from?
The video.
What video? Oh, the homework solution video that I make. In that video, I gave a bonus question. So if you watched it in its entirety, I guess, or if you got lucky and just watched me say that for that 30 seconds, then anyway, that was due today at the beginning of class. Anyone else? No? All right, so I wanted to write down here, I don't know if this is going to come out on screen, probably not, but I wanted to do a quick review of the trig functions. So right now we have sine, cosine, we got that in pre-cal, tangent, cosecant, secant, cotangent, and then for each of those 6 trig functions, if we restrict the domains appropriately, we have inverse trig functions, right? So we have the arcsine, arccosine, arctangent, arccosecant, arcsecant, and arccotangent. So that's a total of what? 12 functions that we learned in pre-cal. And then in Calculus 1, we figured out what the derivatives of the 6 trig functions were, right? That's Cal 1. And then last class, we talked about the derivatives of the 6 inverse trig functions. So if you look at it in terms of functions, right now we have 24 functions. 12 functions along with their derivatives, which are functions also, right? So we have 24. By the end of today, we'll have 48. So we are going to start talking about a new classification of functions. They're still kind of falling into the category of trig functions, but they're called hyperbolic trig functions. That's what today is about. So we are going to talk about 6 hyperbolic functions. It's sine with the little h of x, that's the hyperbolic sine function, the hyperbolic cosine function, the hyperbolic tangent function. So it's just like this, but with an h, and they're not the same functions, obviously. Cosecant hyperbolic x, secant hyperbolic x, cotangent hyperbolic x, and then guess what? For each of those 6 functions, if you restrict the domains appropriately, there are inverses. So you have the inverse hyperbolic sine function, the inverse hyperbolic cosine, so on and so forth. And guess what? For each of those, we can do what? Take the derivatives. And so we'll have 12 more functions after we take the derivatives. Cotangent hyperbolic inverse x. So 12 new functions today. We'll talk about their derivatives, so that'll give us an additional 12. We will have a total of 48 functions, right? And they are all listed on reference page 5 of the formula sheets that you're allowed to bring to the tests. I'm going to ask that you bring those formula sheets. May I? May I? Just like this. You should have them in class with you. All right? So I don't want to say it's a requirement, but it's kind of a requirement, okay? Bring them to class. That way when I'm saying reference page, you'll know what I'm talking about. And the thing I don't want is for you to come into the first exam and you just came from the lab where you printed out your formulas for the first time and you really have no idea where things are on this thing. So you want to get used to using this, right? It's like a tool. And if you look at reference page 5, it's formulas 13 through 36. 13 through 36 give you all of these functions and their derivatives. All right? So you don't have to memorize all of these. There's certain ones you should know. And we could maybe, where did the red markers go? Somebody took them. I think that one's dead. I used that in my other class. Let me see. I've got a good one in here. Pardon? Oh, there's a couple. Okay, well, I'll steal these. All right, so the ones you definitely need to be able to just regurgitate what the derivative is. Sine, right? Cosine, tangent. I mean, your Cal 2 students, this is a shaky check mark, okay? You're going to need to know what that one is, and you're going to need to know what that one is. Those two come up quite a bit, so just know what the derivatives of these look like, especially, check, arctangent x. Know what the derivative of that looks like. And then over here, these, I'd say just be able to go reference those in your sheet. But I think the first 3 here are fair game. All right, so what is a hyperbolic trig function, right? What is it? We know that the trig functions, when we developed those in pre-cal, we started with the idea of like a right triangle, or we did like a circle, and then we defined sine to be like a ratio of sides. But it was all based on a triangle, right? Yeah? Well, it turns out that the hyperbolic trig functions don't really have much to do with it. They are connected, but it's not as obvious. So let me recap something. If I asked you right now to graph e to the x, I hope that we would all be comfortable from college algebra that e to the x looks like that, right? It's an exponential function. It has, in this case, exponential growth. It has an asymptote as you move out the left side, right? The domain of that function is all real numbers, right? You can plug any value of x you want into that. So there's no domain restrictions. The range of that function is everything between 0 and 1, not including 0, right? So that's your domain and range. Now, if we were looking at e to the negative x, how does putting a negative x in there instead of a positive x change the graph? Flips it where? How? Over the x-axis or the y? It's the y. If you put the negative out front, so if I put a negative in front of this, it'll flip it this way. But if I put the negative up in the argument next to the x, then it's going to be a reflection over the y-axis instead. This point right here doesn't move, so that's still here. And then it's going to do something like this, right? And this would not be considered exponential growth. We would call that exponential decay. And it still has the same domain, the same range, right? Okay, so those, you're probably wondering, like, why are you talking about this? We're supposed to be talking about hyperbolic trig functions today. Well, it turns out that the hyperbolic trig functions, the first 6 here, they are all just some combination of those 2 functions. That's what they are. So I'm going to bring up the notes for today, and we're going to take a look at sine hyperbolic first. And you should know that the origin of these trig functions kind of came from the idea that this e to the x and e to the negative x kept on appearing in different situations in the STEM areas, so chemistry and physics and math. These combinations of e to the x and e to the negative x kept on kind of popping up together. And it was so frequent that we kind of had to say, well, look, we keep seeing that all the time. It's got to be important, I guess, right? So let's kind of assign it something. Let's call it something. So we call them these 6 things. So here's the first combination, right? The first one is hyperbolic sine. And the way I said that just now, hyperbolic sine, you can pretty much get away with saying it either way. Hyperbolic sine of x, or you can say sine hyperbolic x. Doesn't really matter which order you put those in. People understand what you're saying. That's all that matters. So look, what do we have here? This, by definition, is e to the x minus e to the negative x. Those were those 2 functions, right? So we're somehow combining them. We're just subtracting the 2, taking the difference between the 2, and then we're dividing it by 2. That's the definition of the hyperbolic sine function. Now, if you don't like the 2 being down here, you can factor it out as a 1/2, and then you would get this expression right here. This is the one I like to work with right here. Got it? That's it. Now, we're going to look at the graphs of these in a second, but just for now, let's just look at the definitions. Cosine hyperbolic is almost exactly the same thing. What's the only difference between sine hyperbolic and cosine hyperbolic? They're being added instead of subtracted, right? That's it. And the way I remember it is that subtraction goes with sine because subtract. That's the way I remember it. And then I just have to remember that the cosine's the opposite of that, okay? So s goes with subtract. I have to just remember the rest of the pattern. Got it? Now, what is tangent? What was tangent back here, back in pre-cal? Tangent, in terms of the other trig functions, was just sine over cosine, right? Well, it turns out hyperbolic tangent is exactly the same thing. It is just sine hyperbolic x divided by cosine hyperbolic x. Now, I don't have it written down here, but I'll just kind of throw it in here. Sine hyperbolic is this. Cosine hyperbolic, I could put right underneath it like this. The 1/2s would cancel, and we would just get this over this, right? And no, right, we cannot cancel, please. We're not canceling these, right? We would just have to leave it like that. And that's what the hyperbolic tangent function is. So if someone gave you a value of x and said, hey, plug in 2 into this function, you'd have to go e squared minus e to the negative 2 over e squared plus e to the negative 2. You'd get your calculator out. It would spit out a number, right? Understand? Questions, comments, concerns, complaints? No? All right, so then cosecant hyperbolic, of course, would just be the reciprocal of sine. So that would look like something like, let's see, 1 over 1/2 e to the x minus e to the negative x. Right, that's what that would look like. And then the 1 over 1/2, I could flip that up and make that a 2 up there if I wanted to, right? But I'll just leave it. And then secant hyperbolic would be 1 over cosine, so I could redo this, but it would be a plus down there instead, right? Okay. And then cotangent hyperbolic is what I had just written on the board a second ago, but flipped over. All right, those are the definitions. I'm curious, can I see your formula sheets again? I'm wondering if they have the definitions of these on here. It would probably be reference page like 3. No. I don't see it. Oh, no, they do. Reference page 4. Right at the bottom it says hyperbolic functions, and it has the definitions of them there. All right? So you're not asked to memorize these, but again, I would memorize the definition of sine hyperbolic and cosine hyperbolic, because there's a pattern there that you want to be able to recognize. All right, so let's take a look at the graphs. You ready for sine hyperbolic? Think it's going to look like a sine function? Not even close. Look. What? That's your hyperbolic sine function. Does not look like a wave like the sine function does, right? Looks completely different. It's not periodic, meaning like the sine function, you had the periods, right? And then you could have like phases and phase shifts and all that. This looks more like tangent, doesn't it? Now, the thing with tangent is tangent had vertical asymptotes, didn't it? And this one looks like it might have vertical asymptotes, but does it? How could you convince me it doesn't? Tangent had vertical asymptotes in pre-cal because tangent is sine over cosine. And any time that cosine was 0, you were undefined, weren't you? So if I look at sine hyperbolic and I look at its definition, is there any x that you could plug in that would make that undefined and cause an issue that would create a vertical asymptote? Oh, this is defined everywhere, right? This is defined everywhere. You subtract the two. This is a well-defined function. You have no discontinuities, no breaks, no jumps, nothing. That means that this graph continues to go out to the right and continues to go up forever, continues to go out to the left and goes down forever. Okay? All right. Now that one, yeah, it's interesting, I guess, but how about cosine hyperbolic? You think it's going to look, you know how sine and cosine were very, very closely related, right? Over here, they were just kind of shifts, like a shift of each other. You think these are going to look close to the same? I mean, the definition, the only difference between them is a plus, right, between the things instead of a minus, right? There it is. What? I mean, that doesn't look anything like the sine hyperbolic, does it? Looks like x squared, doesn't it? This looks like a parabola. But we know it's not a parabola because all parabolas look like this, right? In fact, x to any power, if that power is even, and as long as the leading coefficient is positive, then it should look like a parabola, right, and open up. But I can guarantee you this right here is never going to be any of these because the definition of this function involves exponentials, right? And exponential functions are not power functions. They're not the same. So although it looks parabolic, it is not. And we're going to, at the end of class, study this a little bit more because this is actually a really important function. All right? Hyperbolic cosine. Hyperbolic tangent. There it is. That looks like we might have some what do we call these things when it starts to go up like that and it kind of flattens out and never gets bigger? Horizontal asymptote, right? It looks like this has horizontal asymptotes, doesn't it? Looks like as you go to the right, it appears that the horizontal asymptote is 1, doesn't it? And as you go to the left, it appears that the horizontal asymptote is -1. How would you convince yourself that that's true? I'm saying, how would you convince yourself that this is actually headed towards 1 without actually, like, because what if it's growing just really slow?
Plug in 2.
Plug in 2 into?
To where it would try to spit out something above 1 on the y-axis.
I got you. So just like test to see? Yeah. How did we do it in calculus? If I wanted to know the behavior of a function as I headed out this way forever, what would I actually have to do? Take a limit. Right? I would have to take a limit as x is going first. If I want to test the right side, I'd have to go to infinity of the hyperbolic tangent function, which didn't we just say that that was e to the x minus e to the negative x over e to the x plus e to the negative x? Isn't that what we said it was? And you'd have to try and figure out what this is doing. Shall we or no? I mean, we don't have to. How comfortable would you be with that limit? Let's see. I didn't do this in my other class, but let's see if